for that. Sorry, so that's, I was going to start off with a little bit of like, you know, how many people know who I am? Maybe 2 people. I kind of prefer it that way. And then also, how many people care? And then nobody raises their hand, I say, perfect. So with that being said, thank you for the introduction. I appreciate it. But yeah, I've kind of been collecting degrees for the last 10 years, and I worked at Idaho National Lab all the other days of the year. But today, I'm actually a little bit more focused on what my master's degree was in, so I don't do this yet for work, but it's more control systems focused today, my conversation. And I would say, you know, a little bit of a misnomer. First of all, if you're looking for a cybersecurity talk, please cross over and go see a conversation happening across the hallway. Personally, if I could clone myself and be in it, I would, but here we are, 3 o'clock, ready to learn some stuff. Another misnomer, I guess, about this conversation is that it's not necessarily about control systems, but more so about process engineering and control engineering, which is a little bit more granular. So if an industrial control system is a machine, the plants within that machine are cogs, and on those cogs you have teeth. That is process engineering. So we're going real down deep and kind of annoyingly, and kind of learned this in the last couple of years with my master's degree, and figured I'd share it with folks that if you ever are interested in securing something related to control system engineering, this might be useful. Realistically, I figure most people kind of know some of this stuff, but putting some context to it probably will help out. So generally speaking, cybersecurity is kind of us securing IT systems. They are virtual, they are kind of technology. They have physical aspects, like servers exist, but almost every part of that is kind of on information and, I guess, like virtual systems and their processes. But when we say we have to secure control systems, we have to apply something that applies to virtual systems and then enact it on something that physically exists and has a physical product and a physical repercussion. So it's a little bit of a challenge there. We'll talk a little bit more about that. But yep, ICS. Let's see. I'll skip past that little note. Yeah, that's good enough. Good first slide. How many people made it to that bottom? Awesome. I didn't know if I'd rant long enough for anybody to get there. But I kind of want to know my audience before I do start ranting, because that is my chief trait. Is number 1, I'm a ranter. Number 2, I have imposter syndrome. So we're all here together. How many of these folks in the room are computer science focused or majors? A couple hands, lovely. Any IT, cybersecurity folk, or just IT strictly? Cybersecurity that is not related to either of the 2 things I said? Okay, anybody here actually do industrial control system work? Excellent, couple folks in here. And who did I miss? Anybody that, what do you do, sir? Cool. Anybody else? Nuclear engineering. All right, excellent. So I'm going to sound like a real simpleton today for you, sir, but that's okay. I kind of, as the title says, dumb it down. But yeah, thank you for that. I kind of want to know who I'm working with here. Very general statement. We'll kind of start high and then get into the weeds. Industrial control systems, they're all around us. They make the world work. We refer to them more often as OT. It's a combination of both IT and the actual physical systems to make these things work. Operational technology, in this instance, is systems and processes. The same way IT is made up of systems and processes to make all of our computers and networks and databases and the millions of other things they do work. OT is kind of applied to something where the process and output is not virtual, but more so physical. So, and they have a physical aspect to them. There's a bunch of industries that it works within. I won't list them all, but you can kind of guess the stuff that makes our life comfortable and cush is run by these OT systems. But they're not IoT. Something I get asked actually more often than I think. IAOT, for anybody that's kind of going to want to bring that up, is IoT applied to industrial control systems, but if you take the system, like the actual plant or process out of that, they are just IoT, so I would not consider them on their own an industrial control system. They're kind of a control system, and they have some of the aspects we'll talk about today. Additionally, control systems are complex. Why? Because across sectors, across vendors, across whether it's states, nations, your regulation, how they're made, what software they use, what hardware they use, the understanding of what your limitations are, your safety regulations, all these are different. And because of that, saying you want to secure them is also different. So it's very challenging. If you want to have a nut that is very difficult to crack and perpetually keep you employed seemingly forever, I don't know if we'll ever solve the secure OT systems challenge, because diversity of systems is a huge challenge for us, but it also makes it fun. It's kind of cool to say I know about control systems. I don't know about all of industrial control systems, because as much as I might know about power engineering from my EE masters, I don't know much about water and wastewater from an actual operator's standpoint. I just know what I can read about. So, what's that? Inconsistent. I meant to say inconsistent. Thank you for catching. You know, I proofread this with 4 different people and not one of them caught that. It should have been 5. I appreciate that. Yeah, inconsistent across sectors, locations, vendors, countries, industries, nearly anything else. This does create a challenge. Appreciate that. So, this is more so, this is the only time I'll be talking about hardware. A lot of people, when they talk about OT, they're like, oh, you have PLCs and HMIs. I'm not talking about that. We're going deeper, for better, for worse. But generally speaking, you kind of have a couple of classifications here. PLCs, most people have heard of these. Who has heard of PLCs? Many folks. Look at that. If I had said that like 8 years ago, I wouldn't have even raised my hand, let alone half the people in this room, maybe not. So it's becoming more common. Realistically, our real-time computers and PLCs are kind of becoming one. They used to be a little bit more separate, but your average PLC put out by a vendor is running an RTOS now. So that's kind of becoming one. Microcontrollers, essentially very pared down computers. They do have a command shell, but they're very limited. They're faster than a PLC. By nature, they're very much pared down. If you want to get even faster, which we'll talk about like process time and loop time, but you want to go faster, you can go to an FPGA. It's essentially a piece of hardware that's customizable to have logic arrays, logic blocks, make decisions for you as you see fit. And based on what your input and output are hopefully going to be, you kind of get to choose how this chip reacts. And then the fastest super turbo, I call it, is an ASIC. Anybody that's ever used like a voice recorder takes an analog signal and in real time, nearly real time, converts it to a digital codec, through a digital codec, creates a digital file, streamlined in real time. That is a chip that is considered probably the fastest way to have a control system reaction. So that is the last of our hardware talk. And now we'll actually talk maybe a little bit more about control systems and how they're applied. So, classes of control. Most of what we'll talk about today is continuous. This is what most of us, I guess, would understand as a control system. Continuous, generally speaking, you have infinite granular control over what we call a manipulable. And you can have, you have a high point and a low point, but within that you have limited options of what you can actually adjust on that. Then you also have the opposite of that. This is the other, I'd say, most common, and what we'll talk about is bang bang. This is essentially, I'd say, a binary output. You kind of have an on or an off. The best way to compare these is if you use a stove and it is a gas stove, you have a knob, on or max, or sorry, off or max. If you have a flame really small, you can adjust it perfectly to where you want it to get the right temperature. That is what I would call a continuous control. Whereas bang bang would be more of an electric stove. So anybody that doesn't know how electric stoves work, they essentially turn on until they hit what you want them to be, and then they either switch to a smaller coil or they just turn off and then come back on a minute later to retain what they can of that temperature, right? So we'll go a little bit more into detail on that, but 2 that I figured were worth mentioning are model predictive. So this is used, I'd say, mostly in modeling and scientific purposes. I'd say not in a physical realm. This is essentially saying I want to build a control system. I want to do the math to calculate what will happen. I want to have inputs, outputs, essentially writing a computer program, but doing some form of simulation to see if I can prove my control system will react how I wish. Great example is that Tesla likely had something like a model predictive system for a long time, making sure that they would not run over cyclists and motorcycles because they do not look like cars. They did as much as they could to simulate, have a model to prove the system would work with their sensors and whatnot on the cars before they actually put it on a car, ran it, and said, let's see if it works, because you will find out very poorly if it does not work. Yep, I'm glad somebody said it, but either way. And then adaptive, finally. Adaptive, I'm actually not going to give too much on. This is, I'd say, almost exclusively a research/scholar type control system to work on. The theory here is pretty much every time you are running a phase in your logic loop, the entire parameter of your existence changes. So you could kind of call it like quantum physics for control systems. Super beyond my capability. I have no desire to go into it, but it's interesting, worth kind of noting and mentioning. So this is our plant. Literally there's a plant, but also we'll figure that we actually call this a plant. So this will kind of be my reference point. This is by far the most simple version of what I could consider a control system, if not like a light switch, but what we would kind of formally refer to as a control system. I'll come back and reference this a bit. So in this, we have a water level sensor, a water pump, a water tank, there's a little plant. It's a hydroponic system, so it's growing. The roots have overgrown into the water, neither here nor there. And then there's a little water line that pushes water up into a watering tray. Very, very simple, right? But the plant itself is a physical space in which your processes can function. Some plants have one process. Most plants have dozens of processes within one plant. But the plant is a physical space, whereas processes are I'd say virtual, if not mathematically representable thing going on. So a control system has many processes, many plants with processes within them, one-to-many relationship. In this case, every process should have a control variable. In our instance, what I'll refer back to is the water level of this tank. We'll say that it is at 4 inches. It's measured at 4 inches, and we want it to be at 3 inches. We'll go a little bit deeper into that. Every process, at least if we're using something that is a closed loop, which we'll talk more about, we'll have a feedback option. In this case, that is provided by our water level sensor. It can tell us where we're at, so we understand where the status of our process is as an output. Used for modulation. We have a reference, which in our case, we also refer to this as a set point, but it is what we wish our actual control variable was at. Like I said, we wish it was at 3, we want it at 3 for some reason. Usually your reference is provided by scientists, subject matter expert, engineers, people who understand their topic very well. If you're working in a plant where you're mixing chemicals, you probably have a chem engineer, and they're going to say, well, you should have exactly this amount parts per million mixed at this rate with this temperature, many things going on, and they can tell you why you really wanted to know. But as a process engineer, your job is to get to that actual reference point, because the people who know what it means told you to. And then finally, a manipulable. So manipulable is the actual physical thing we can put power or take away power into to control what's actually happening and potentially modify. Again, get our control variable as close to reference as possible. In this case, it's a water pump. So very, very simple system. For what it's worth, any industrial control systems you might be imagining are this times, like, we'll say anything from 10 to 100 as far as complexity. So we only have one thing to control here. But I mentioned set points, and I mentioned that there are larger control systems in the world, so I'll give you a couple examples just to give like reference of how this would apply in the real world. So you can imagine power transmission. In this case, we'll say line voltage would matter. So if you had power going through a line and a squirrel touched it incorrectly, or it touched a tree, or something fell on it, and you're measuring through feedback what your line voltage is and it goes to 0, smart thing to do would be to open a relay somewhere, cut power to that line, protect from a fire or an arcing or something like that for the safety of your system and also the safety of anybody in proximity to that system. Water treatment. This is something that anybody that's been following cybersecurity for industrial control systems in the last couple of years would know. Oldsmar had an incident where there was chemicals, parts per million, being modified in the plant illicitly. You kind of don't want to have too much or too little of any given particulates in any of your water, right? That's how I don't know how you work. That's how I work. Oh, I lost one. That's good. So this is supposed to say Ola natural gas on the left. Thank you, PowerPoint. Appreciate that. Making sure your ONG, your fluid, can actually flow as necessary. Oh, perfect. Thank you, Microsoft. Medical, anybody that has or knows somebody with a diabetic condition, if you have an insulin monitor, quite important to monitor your blood sugar level and have something, or insulin pump, modifying what your blood sugar level is accordingly. And then building control, the fact that this room is at a comfortable position. I don't know if you guys are too warm or too cold, but the fact that we're looking at the temperature, adjusting accordingly so we're not freezing or sweating. In industrial instances, you might be worried about what your humidity is, what your CO2 levels are. In a home, you probably care about that too as well. But there you go. That's a couple options, or a couple examples. And I will take a second because I've been ranting for a second while I drink water. Does anybody have questions? Yes. That means I'm explaining so perfectly that nobody has anything left. Oh, I'm sorry. My apologies. That's a great question. I would say it's up to, if you're the dummy, are you building your own process or are you building for somebody else? I'll answer your question with a question. Because if you're at home, I say that to say this, right? Say you want to build something to like feed your cat. How much should your cat eat every day? You can measure the weight of the bowl. And you say it should have 5 ounces of food at 6 a.m. every morning. And you take whatever the current weight is, minus 5 ounces, invert it. And then pretty much dump food until, depending on how you apply it, right? There are practical, obvious times where sure, this is what my set point should be. But realistically, it does take a bit of a team. You have to have one of those smart people that can tell you, well, my line voltage should never exceed this many kilowatts. Or if we're trying to do a load balancing, realistically, power engineering is all about balancing. It's a nightmare. So it's never actually at ideal. But you might have to have an environmental engineer to understand, and we'll talk about this a little bit when we get to noise and disturbances. Yeah, so it's all about the complexity of your system. If you want to build something at home, congratulations, you're a subject matter expert. If you're trying to get something a little bit more complex, you're gonna have to call a couple friends and perhaps do some homework, get somebody who knows differential equations on your side, because yeah, it's just the way it goes with tuning and whatnot. I appreciate your question. Any other questions? I apologize for missing your hand. Cool. All right, basics were basic. We've made it this far. We'll kind of go to a couple more advanced applications. Not advanced, but how do you actually use this, right? What does it matter? Because we've talked about something super simple. We'll talk about loops. We'll talk about feedback and feed forward. We'll also cover 3 things that kind of make those first 2 necessary, and then PID tuning. So these are the, after understanding the basic terms. Disturbances, as we just said we cover. Disturbances are inherent, we'll say, principles or facts about your process that you don't necessarily get to control, but you can observe. If not, you are putting in control to get around your disturbances. So, for the purpose of our example here, the water might pump up to your tray there, but it can't really control how quickly it pumps down. Or if we're doing an array of pumps, and they're pushing into each other, you can say maybe, well, I can control the rate at which water leaves my my tank here and goes to the next one, but I can't control how quickly it's coming in, or if water is sloshing, evaporating, something like that. There are instances of things that will modify what you want to happen, and you're doing your best to work against them. Noise, on the other hand, is inevitable, and you kind of just have to work around it. So noise is introduced by, realistically, poor sensors. So I built this system. It was a little different. I just had to draw something real quick, and that just worked. But I built this system. That is an Adafruit sensor. It costs a whopping $10. If I went down to the water company and said, I will measure your water level, let me get my $10 sensor out, they would laugh at me, and I would laugh at me because I sound silly, right? So the more money you spend on a sensor, the more accurate you get. When I say accurate, I mean not only can it be correct, but it will not have disturbances of its own where it kind of jumps to 1,000, drops to 0, because our system is going to try and react to those numbers, and also how quickly it can give us an actual reading. So timing and accuracy are hugely important. This is a very unimportant system, but if, again, we're working in a chemical plant, we're mixing volatile things, we want our sensors to be pretty exact for the purposes of not getting in trouble, right? So stability is ultimately the goal of any system. You can say, oh, I'm going to have these inputs, goes through a system, I get outputs. Anybody with codes knows it's kind of what you're hoping for, and then you run into a bunch of errors. You have to figure out why is it not working, right? So we could build this system, and then for some reason my water line goes to a different plant. That wouldn't work. Logically, it wouldn't work. So it's generally speaking how much you can measure that your plant does its job. And then your sensors and your actuators, these are another fancy way of saying the inputs and outputs. So what can measure how you're doing what you're doing, and what can help you change what is going on to get better on, or to further, reduce your error, which we'll get to in a second. Sweet deal. So now we get to discuss loops, arguably the thing that makes control systems work. Both of these are used equally. I would say, if you want, we can talk, I guess, a little bit about when you would implement each, but open loops are more simple, so we'll start with those. Anybody that codes, again, this is going to be pretty rudimentary, but the logic there is underlying. So an open loop removes much of the nuance of how you control system. There is no feedback in an open loop. Generally speaking, it is a force control, so you kind of set an input, and then it just goes into perpetuity until something interrupts it. So pretty straightforward. There are instances where this is nice, like an override or a safety control. Instances where this would make no sense, like on something where I have to know how much water is in it. But the output is independent of the input, lacks reference to it, pretty self-explanatory. Reference input goes to controller, actuated input. There's no loop in this at all. It's a straight line, right? So an example of this is a light switch. Turn a light switch on. It doesn't know if the light's on. It just changes state. Maybe it's getting power, but the light switch doesn't know if there's light coming from the actual bulb. On the other hand, a closed loop feedback system has something to measure and provide feedback. So after single process loop, output is returned via a sensor, and it forms the next process input. And we'll talk a lot about closed loop much more today than open loop. It's fairly simple, very simple concept. It's only as reliable as the hardware it uses, which we've alluded to a little bit with the sensor reliability, but also your actuator reliability. And this is the logic of how that works. A little bit more complex, ish, but we'll go into this a little bit detail. But you notice there is a feedback loop to go back to the beginning. And this just runs into perpetuity with the input and the output changing as we go. So, as promised, we'll talk about this a little bit and apply some of the terms that we learned to it. At this point, so your reference input, that is what we call the control variable. So this is what we want things to be at. This is our set point. This is me saying, I would like my water to be at 3 inches, please, process system. And this is what I've embedded in my logic to say the feedback hopefully should be at 3. However, I don't always get that, right? So error is a measurement. It's the difference between your reality, my water is at 4, that is my, it's actually in the far right, your output, but we're going to assume for this instance we've already done one loop and I have the feedback saying water level's at 4, what do you want to do about it? I wish it was at 3, so our error is 1. Pretty straightforward. The goal in all processes is to get error to 0. Pretty simple, but sometimes the world gets in the way and there's lots of noise in there. The actuator is our controller, pretty straightforward. It's also tied to the manipulable. Since they're considered the same thing, we're going to say those are tied logically. And then our control variable output, kind of alluded to this earlier. So this is where we're saying we've measured it at 4. We wish it were at 3 because it's not. We've turned on our actuator via the controller. Controller essentially, in this case, is me closing a relay that gives power to the pump while pretty much it's if you're writing this in code, like while error not equal to 0, you have to figure out if it's positive or negative. Then you would say close this loop, essentially turning the pump on, pump water until error is 0. And then the sensor reads that and pretty much says, cool, so now we're at 3.7. We've gone down 0.3 inches. Gives that back to our error detection. And so now our error is 0.7 instead of 1. And it does that a couple dozen times a second until it can get from 4 to 3. And our error goes from 1 to 0. So, like I said, fairly simple concept, but these are just putting all the fancy terms on it that would apply to control systems or process engineering. So, now we'll discuss feedback. Instead of using bullet points or graphs, I'll just tell a story with this one for the sake of kind of getting the concept across. Imagine you're on your way home from vacation and you arrive home. It's been snowing for a week. Well, we all live in the area we live in, so I imagine we all understand this. And you walk in the house and you say, "Whew, it's cold." And you run over to the thermostat, turn it on, and about an hour is what it takes for your home to warm up, and you go, "Thank you. I can take the 5 jackets and the 3 pairs of socks off and enjoy a cup of cocoa. Good for me." That we would kind of, boy, if I had to say you're using feedback, does that kind of make sense? You come to a place, you measure too cold, you turn on a heater until it's not too cold. Pretty straightforward logic. How would you go about solving this issue better, right? If our reaction time is an hour, kind of not great. So we'll flip it and say you're driving home, you're about an hour from the house, and you say, "Well, it's been snowing all week, and I'm pretty sure the house is too cold." So you log into whatever your smart thermostat app is. Hopefully you have that on a guest network or something that is not on the rest of your LAN. Security people, please implement security in your network. And you say, "Cool, turn on the heater because I don't want to come home to a cold house." And then your thermostat plugs away, you get home, and you're like, "Oh, look at this, my house is nice and toasty. I don't have to wear 3 jackets. I don't have to have 3 pairs of socks on. Get to enjoy my cocoa and read a book." This is what we would call feed forward. Feed forward in concept is pretty much preemptively guessing or assuming things about your environment that inform how your process will work. So, it's not necessarily that you've measured and you went on the app and you said, "I know it's currently 50 degrees in the house and I don't want it to be." It's just, it's been cold, so I guess I'll turn it on. So the logic is more so in the fact that you acted before you actually had to observe and get feedback, and that you're not using a feedback sensor to make these decisions. You're just using realities about your environment to kind of pre-inform how you should be doing this. In reality, a finely tuned system will utilize both of these. It will have some feed forward to correct for just assumptions about your environment, whether it's ambient temperature or the rate at which things evaporate, or knowing that maybe my water is dripping from that tray in the little water hydroponic system. It's dripping at 3 tablespoons a second, so I kind of have to have the pump on at 3 tablespoons a second, whatever the equivalent is, just to correct for that thing that I'm not measuring, but I know it's happening. And then in addition to that, using feedback loops, which we've already discussed, to actually have the process function. So that's feed forward and feedback. Hopefully my very simple story there kind of gave the concept there. And this is our final, at 31 minutes, I'm only going a little fast. Our final kind of thing to cover, PID. So PID and I go way back to about a year ago. How many here people? Who knows about PID? Okay, I'm sorry. It is both beautiful math that makes things so elegantly work together well, and also an absolute nightmare to tune and describe, which I'm going to now attempt. So, wish me luck. So PID, it's a 3-phase algorithm, has 3 separate chunks. It's built itself, so you can have, it's essentially a way of tuning your response to be accurate. Because it's one thing for me to say I have a pump that turns on, but I can't control the rate at which the pump is pumping. Can't do anything about overcorrections because I can't put water back into the tank. I can't control if there is a leak or anything like that. So PID takes all this noise and all these disturbances and finds a way to make everything smooth so it doesn't overreact. You don't end up with a messy process. And again, when we're talking about a hydroponic system, not a big deal. Talking about maybe what makes the power stay on here. You don't want to have too much saturation on your line. PID is incredibly important. So the first letter there, as you can read, we can all read. Proportional. Sweet. This is essentially the basic of logic. You got to reduce error to 0. Do that as best you can. Do whatever the thing is to get that from 1 down to 0, or if it was 50 or whatever your sensor measures. to get it to 0. Does not take noise bias into account, and it can cause wildly inaccurate responses if you have too much noise or unaccounted for disturbances. So you get erratic behavior. You get a pump that's pumping too strong, and you end up flooding the tank or something like that, right? Weighs all air equally, so you kind of have to modify your sensor's gain to maybe get this to be a little bit tuned, but yeah, it doesn't really take any noise into account on your sensor. So that's step 1 of any tune. We already talked about this. This is pretty much everything uses P. So PI, I'd say this is more getting next step up, most commonly used if you wanted to get a system to react pretty reliably without doing a ton of math and tuning. But PI adds the integral portion of this, adds up all your errors over time to kind of get like a average to smooth out if you're pretty much got a sensor and it's just reading erratically, sometimes accurately, but then it jumps to 100, and then jumps to 0, and jumps to 100, jumps to 0. The integral portion takes this, smooths it out, so you get more of what we call just a smooth read on your actual sensor. So this will slow your control down though. It slows down your loop every time we're doing that feedback loop, however many times a second. Now I have to do mathematical calculations on that, and it slows your ability to respond to erratic behavior. Takes here, what else did I not cover here? Reduces extreme reactions. I'm pretty sure I covered that. All right, now this is where it gets fun. Derivative. Essentially, anybody here that likes doing lots of math, this is a double derivative. You're not only taking error, binning it, then looking at over time, averaging your time response, compares your errors in a time step, from time step to time step, and almost uses that as a prediction to kind of go against significant actions, or rather only make significant actions when there is a notable change. Trying to think, yeah, I figure that's worded pretty well. Prevents correction, overcorrection over time after P and I have been established, and it's acceleration and deceleration control. So it's a bit more predictive. For instance, if I have a pump that is pumping too heavily, it'll kind of take that into account and say, I know the sensor's reading that it's going to go pretty erratic, but we can already correct for what your output is based on knowing how your actuator has been behaving and what the sensor is reading based on that. So that was my best job I could do at PID. The fun thing about this is that in itself it is tunable, so you can add weights to each of these letters and say, well, I'd rather have, in this process, I'm getting a better response when I'm putting a higher weight on the I in this instance and not so much on the D. Or, like I said, some folks won't even do the derivative, and they'll just use PI tuning. Or you do lots of proportional because you have a killer sensor and nothing ever is measured incorrectly, but then the integral is just there for kind of smoothing it out. But PID is applied mathematically to any process that you would like to have a smooth response on, both in power, in water, in chemical, making sure that your sensors are pretty much working in line. What is worth noting here is that it will only work, or works only effectively, we'll say, without burning out a relay, on systems that are continuous. So we have continuous and bang bang. The idea that I need to have adjustments, my only options are turn it on or turn it off at a certain rate. That binary, I've actually burned through relays trying to do PID tuning. It was a cheap relay, it was like 30 cents or whatever. The same one that everybody else uses on their Raspberry Pis. But that thing was just going and burned it out. It was great, it smelled bad. But you would want, in this case, something that gives you a continuous control. So a voltage controller or a current controller, something that you can modulate. Or if I wanted to say, I'll purchase a pump that has a third or fourth wire to change the flow rate of the pump instead of buying a fixed flow rate pump and trying to use the power modulation of that pump to control it, I buy a pump that I can control. Or a valve that I can have multiple positions. I don't want to have a valve that only has open and only has closed. So PID tuning exclusively works with continuous, obviously in feedback. So that is PID in a nutshell. You're allowed to ask me questions about PID, but I wish you wouldn't. Full disclosure. There's always one. it does introduce complexity, and it does work better when you have more than one process in a system for the or in a plant for the purpose of them balancing each other out. So there is a balancing act within your sensors and actuators per process, and then a balancing of processes within your plant as well, so that they don't override each other or kind of over whatever action or inaction they're taking doesn't sabotage the others. You got a question as well? Okay. It's fair. Yes, that is. You better trademark that. Awesome. So now I'm just going to go quick conclusion. I'm only 5 minutes too fast here. But what we learned, we talked about hardware options, basic terms of process control or process engineering. We applied those terms to a very simple system, hydroponic system that only has one thing going on, and even then it's kind of poorly designed. Discussed examples of these being implemented in different plants across different industries, expanded on those examples using the loops, feed-forward feedback, and talking about noise disturbance. And then we touched on PID, which hopefully I actually described that in a way that was useful. That being said, I want to give a thank you to Dr. Jacobo Robertson. He is my mentor and PhD advisor that I got my EE through. George McCrackus, anybody that knows George, he's a powerhouse of inspiration and knowledge. If anybody ever wanted to just feel empowered to get something done or learn more, George is the person to call. And of course, Ginger Wright for inspiring me to submit a talk and actually give a talk on my own volition and not because work asked me to, which I usually would not have done. And also you all for your time, your attention, for choosing me over the car hacking, which I don't know why. So yes, with that, questions? Of course. Who here knows what an SIS is? Sweet, we got two. SIS, essentially controls for the purpose of enacting safety. So we'll give an example. We'll go back to the chemical plant, right? Say we have something we're mixing in a volatile tank, and for some instance, something goes wrong and it overflows, or it's giving off a noxious fume or something like that that kind of messes with people's ability to continue living. Not only is that process functioning on its own and in its best bounds that you can program it, but there are systems outside of it that are doing their own job to measure, like I said, CO2 measurement or moisture measurement. So if, for instance, it overflows, and there are sensors surrounding this particular tank that can say, we measured that there is water, sound an alarm, or there's moisture rather, sound an alarm. There should never be moisture in this environment. There is, so I'd say for power, there is both, we'd call it process safety as well as physical safety, lockout, tagouts, firewalls, things like that to prevent people from getting shocked. But in addition to that, there are systems within your substation that, at least in some substations, if you are present and still operational, they'll pretty much do like a kill switch. But yeah, the idea of industrial control systems in itself, or at least a process, can be implemented in not just to make a thing, but also make sure that the plant itself is protected and the people surrounding it are protected. Especially the bigger your industry is on a physical level, the harder it will fall. So a plant that is 3 stories tall will also explode 3 stories tall if it's not treated correctly. So that's why we have the similar principles applied to safety instrument systems. Appreciate that. Hopefully that was a decent answer. Yes? Don't quote me on that because my brain mixes up acronyms so bad. I have dyslexia, so I'm mixing up. Ideally, yes. I would say in a perfect world, I would observe those on separate networks. Anybody that has worked with control systems long enough to know most of them were built when flat networks were just cool and kosher and sweet, and now we're kind of saying, please segment, and or put some firewalls and separation here. to for the recordings, in case they didn't pick up Zach, essentially saying as time's gone on, these systems used to be very separate, entirely analog, entirely digital, and as the redundancy built, the fact that there were two things doing the same thing, we've integrated, however, security implementation and awareness has not always been where it should have been while integrating these systems. So even though we do have TCP/IP-based control that was built in the 90s, they probably didn't know that there were security controls to be built into that, and you kind of have to do your job to, you can't really retroactively break the system, so they tend to just put them in their own segment until they get replaced. So. Mhm. The methodology. Okay, so I want to go to this from a statistics point of view, but that's not what we're doing here. So I'm trying to think from a control methodology standpoint, what keywords would you use? I actually am uncertain. Do you have a control set? So have you done this in the past? Did you measure previously different smokers, how they've reacted? Or are you trying to say, just based on this one time, you're measuring your temperature and you want to know when it'll start at this and when it'll get to that? Mm. Yep. I don't know if it's as much of a control systems question. At least my brain won't answer it that way. I would say maybe do like a multiple regressive prediction if you can get, on your time series or in your time, because it is a time domain or time domain function issue, which calculus could help, but also no. Excel can answer that question for you just using statistics. And I apologize if there is an answer that I should have known. My apologies to Dr. Robertson for not knowing that one. We all set? No, yeah, no, cool. Precision versus accuracy. Ideally both, but that's not an answer. Um, in this instance, truly, sadly, I'm going to plead the fifth because I cannot give a good answer to that. That is beyond my abilities on sensors. Yes, who does have an answer? That is a great question. Perfect. I have no qualms with that answer. I greatly appreciate you stepping in. Oh man, it's heating up in there. Awesome. Any final questions? All right, we made it out alive. Cool. Thank you all.